times b n prime tilde. So in order to do that, I'm not sure you can see the blue chalk as well, so I'm going to continue in white chalk. Actually, I can do this at least in the blue chalk. So what we'd like to do is we'd like to invert this. I don't have to invert it. I could use what we know already. We know, for example, we know that the amplitude ratio is the magnitude of g of I omega. So let's see what that is. That's just equal to 1 over a I omega magnitude, which is just 1 over a omega. And we also know that the phase lag phi is the arctangent of the imaginary part of g of I omega over the real part of g of I omega. So let's see what that is. The g of I omega, so this is the I'm not sure, can you see the blue chalk or should I move on to white chalk? Use the white chalk? Okay. So the imaginary part, it's, so let's recall again that g of I omega is 1 over a I omega, which in order to get the real and the imaginary part, I need to bring I to the numerator. So I multiply top and bottom by I. And then I get I times minus a omega. So notice the imaginary part is minus 1 over a omega, and the real part is 0. The imaginary part is minus 1 over a omega, and the real part is 0. So what does that tell me? That tells me that the imaginary part of the real part is minus infinity, because it's this over this. So this is the arctangent of minus infinity. And let's just look for a second at what the arctangent looks like. The arctangent function, so here is pi over 2, here's minus pi over 2, and this is 0. The arctangent function looks something like this. Why is that? Because let's look at the tangent. The sine of the tangent is sine over cosine. The sine of pi over 2 is 0, and well, let's just, the sine of 0 is 0. The sine of pi over 2 is 1, and the cosine of pi over 2 is 0. So that's why I get infinity at pi over 2. The sine of 0 is 0, and the cosine of 0 is 1, so the tangent of 0 is 0. The sine of minus pi over 2 is minus 1, and the cosine is 0, so I get minus infinity. So what I find here is this is equal to minus pi over 2. So we just determined that directly from what we learned earlier, that for the amplitude ratio and for the phase lag, but we can also, in this particular case, we can do the inversion directly. So to do the inversion directly, we look at the S dependence here. So we have m omega over a coming along for the ride, and I'm just looking at the S dependence. And because I have a cubic in the denominator, I have 3 roots. So I need to use partial fractions in order to break it up. And to do that, I'm going to multiply through by the denominator. And I have 1 is a times s squared minus plus omega squared, plus b times s minus I omega, plus c times s plus I omega. Where what I did is I just multiplied through by s squared plus omega squared. And now I equate like powers of s. So for s to the 0, I have 1 is equal to, well, a omega squared. And then here, everything has powers of s there. So a is equal to 1 over omega squared. And s to the first power, well, the no s to the first is here, but there is an s to the first here. So this is equal to b times minus I omega plus c times plus I omega is equal to 0. So I can cancel out the I omegas, and I have that c, I bring this to the other side of the equation, it tells me b is equal to c. And if I look at s squared, I have 0 on the left, but on the right I have a s squared plus bs squared plus cs squared. Okay, well, b is equal to c, so this is equal, and a is 1 over omega squared plus 2b. So this tells me that b is equal to minus 1 over 2 omega squared. And c, and this is the same thing as c. So what does that tell me? That tells me that 1 over s squared plus omega squared is equal to a over s squared. So a is 1 over omega squared. 1 over s. Plus b and c are both the same. So that's minus 1/2. And then I get 1 over s plus I omega plus 1 over s minus I omega. Where, again, all I noted was that a is 1 over omega squared, and b and c are minus 1 over 2 omega squared. So I factor out the 1 over omega squared, and I put the 1/2 there. And I can combine these. This is 1 over omega squared times 1 over s, and then I have minus 1/2. And now I bring this under one denominator, s squared plus omega squared. And I have s minus I omega plus s plus I omega. So the I omegas cancel, and I just go to 2s, and the 2's cancel. Okay, so why don't we now go through the rest of the inversion. With the rest of the inversion, I have a omega, so I have m omega over a times 1 over omega squared, 1 over s minus s over s squared plus omega squared. And let's invert that. This thing is L prime tilde. So therefore, L prime of t is equal to. So to do that, we need to go to our sheet with the inverses. And we can notice that, so that this comes along for the ride, m omega over, well, m over a omega squared, a omega. If you want to do omegas cancel. And 1 over s, we see just gives us from line 3, if you like. 1 over s to the first gives me t to the 0 over, which is 1 over 1 factorial, so just 1. And s over s squared plus omega squared, if we look at line 12, that just gives me cosine omega t. So what we can, so here we actually, we can actually do the inverse exactly, and we can also notice that from the half angle formula, if you remember from high school, the sine of x over 2 is equal to the square root of 1 minus cosine x over 2. So here I have a 1 minus cosine omega t, so that's just equal to twice the square of the sine. So that's equal to m over a omega times 2 sine squared omega t over 2. And what can we see here? Let's just check to make sure that what we found using the general formula is exactly correct. So the first thing we can notice is that the frequency of the input frequency, which was omega, is also the frequency of the output. The sine of omega t and the cosine of omega t, since it's the same omega, they have the same frequency. How about the amplitude ratio? The amplitude ratio is the amplitude of the input over the amplitude of the output. Amplitude ratio is the output over the input. So the output is L prime tilde its magnitude over the in prime tilde. L prime over the in prime. Well, L prime, the magnitude of this, so I've got an m 1 minus over I omega, and I have 1 minus cosine t, cosine omega t. And the input is m sine omega t. Well, the magnitude of this thing, the magnitude of the sine, goes from 0 to 1. It's the maximum that goes from 0 to 1. So clearly this thing has an m here. And I'm not going to go into the magnitude of the sine squared goes from 0 to 2. So I'm not going to go through that calculation in great detail, but you can see that the m's are going to cancel, and I'm going to have an a omega in the denominator, which is essentially what I have here. What I would like to go through, however, is the phase angle. And let's just notice that the sine, m, the input, v in prime, which is m sine omega t. So the sine starts here. And let's notice the output. The output is 1 minus cosine. So the cosine, so the sine of 0 is 0. The cosine, what's the cosine of 0? How about some audience participation? What's the cosine of 0? 1. The cosine of 0 is 1. So 1 minus the cosine of 0, 1 minus cosine is just 0. So let's look at the output. I start out at 0. But let's now go to, so let's now look when omega is pi over 2. When omega is pi over 2, then sine of pi over 2, omega t is pi over 2. When the sine of pi over 2 is 1. So here we're on our max. And what happens down here? Well, the cosine of pi over 2 is 0. So this here I just have a 1. So this is value 1. And let's look at what happens at pi. At pi, the sine is 0, and the cosine of pi is minus 1. The cosine of pi is minus 1. 1 minus minus 1 is 2. Okay, so what can we see here? And why don't we just go one more? If I go one more, when I'm at 3 pi over 2, the sine of 3 pi over 2 is minus 1. The cosine of 3 pi over 2 is 0. The cosine, so I'm back down to 1. And here, when I go to 2 pi, I just get, again, 0. So what can we see? What we can see is that the maximum here is comes at a different point from the maximum here. And in fact, there's a difference of 3 pi over 2. That is, this input then leads me to this, let's see, is that sort of obvious from here? That doesn't look, it's not as clear from this picture what's, that is 3 pi over 2, but let's see if I have anything in my notes that might help with that. No, I'll have to get back to that. Well, we weren't able to show directly from here that phi is the arctangent of the imaginary over the real part. I'm sorry, no, here we had phi is minus pi over 2. So that's actually correct, because I had minus pi over 2, not 3 pi over 2. So, yeah, what we can see is that there's a difference of pi over 2 between the input and the input maximum and the output. So there is a difference in pi over 2, as we found up there. So it was indeed minus pi over 2. Are there any questions on that? Okay, well, if we're looking at the stability of feedback control, what are Again, make sure you sign the attendance sheet because those people who didn't show up today lose a grade. There will be 1 grade lower. So it's very important you sign the attendance sheet. There's no excuse for cutting class. Okay, so in the design feedback control, are you not? Oh, you don't have your tripod? That's okay. So we're interested in the stability of feedback control. Obviously, our goal is for our system to be stable and hopefully at the set point. So, in understanding this, what are our goals? We would like to design a system that's in fact stable, and we would like to know why the tuning constants that we choose by, for example, this method. We'd like to understand sort of the shapes of these curves, why the shapes are what they are, and we would also like to be able to understand how, if we know the stability of the system with no control, how that influences the system with control. We'd like to understand this connection between the control-free system and the system with control. So what we're going to do the rest of this hour is we're going to talk a little bit about the relationship between the open loop system, the system without control, and the system with control, and we're going to look at how we can actually do stability. Okay, well, just a little bit of a refresher. If we have an ordinary differential equation, and let's say we have, say, an y to the n, n derivatives of y plus an minus 1, n minus 1 derivatives of y. This is the number of derivatives. Plus plus a1 y prime plus a0 is equal to some forcing function f of t. So this is sort of the form of our systems, where typically we've had either first-order systems or second-order systems, where the largest, highest derivative is either 1 or 2. But of course, if we have n CSDRs in series, the highest derivative would be n. And we noted that on the right side, when we did all of these problems, on the right side we had either had our disturbance or we had the action of the controller. So if you remember, on the left-hand side, we had things that only depended on the system, on the structure of the system. And on the right side, we had things that changed. When we were in prime variables, we had the disturbance, and we also had the action of the controller, the manipulated variable. D prime and MV prime came in here. This D prime and MV prime came in here, but this was the system only, the system itself. And we noted that when we take the Laplace transform, if these are prime variables, we noted that when we take the Laplace transform of this, that this gives me an s to the n plus an minus 1 s to the n minus 1 plus plus a1s plus a0 times y prime tilde is equal to f tilde. And if we're looking at y prime, remember y is the variable we're interested in, the dependent variable. It's typically the control variable. We noted that y prime tilde was equal to f tilde divided by this polynomial, an s to the n plus an minus 1 s to the n minus 1 plus plus a0. Now why do I go through this? I go through this because if you remember, if we're interested in the stability of y, we're interested in the stability of y prime, or y, the control variable of the system, then we noted that the stability of the system depends only on the denominator. System stability depends only on roots of denominator. as long as f of t does not go to infinity. As long as the disturbance doesn't become infinite, or the manipulated variable doesn't become infinite, the system will be stable if the system itself, if the denominator has roots that all have negative real parts. So what that tells me is, remember, we defined what closed loop stability is if we have a bounded input, then we get a bounded output. So what this is telling me is, if I have a bounded input, t prime and v prime, the system will be stable if and only if the roots of the denominator have negative real parts. So, system stable if and only if. So stable is by this definition, closed loop stable. If and only if the system, the roots of denominator that come from the system only, have negative real parts. No positive real parts. So the most direct way of looking at stability of the system is to look at the roots of the denominator in any given situation. Any questions on that? And let's just notice what that would look like. So for example, if, so let's look at different situations. If the roots are a plus ib, so here's a situation where a is negative and b is 0. So here I'm looking at, say, the output y prime. Another case is where a is much less than 0 and b is 0. So let's make this a little more gentle. And this is a situation where a much less than 0, then it goes much quicker. How about a less than 0, b not equal to 0? Then it can oscillate, as is the case, because b is not 0, so there's an imaginary part. What happens if a is 0 and b is not 0? If a is 0 and b is not 0, then it just oscillates and doesn't decay. And of course, what if a is greater than 0 and b is not equal, and b equals 0? Then of course, it can just explode. And a greater than 0, b not equal to 0, it oscillates and explodes. So these are the different possibilities depending on what the roots look like. Are there any questions on that? Okay, so again, let's refer back to this, and let me just remind you of what CV prime tilde looks like. So CV prime tilde is, I have a denominator that's 1 over 1 plus GP, GV, GC, GS. And that's multiplied by GP, GV, GC times SP prime tilde plus D prime tilde, GD, D prime tilde. So we can notice that both of these have the same denominator. And I'm going to refer to that when we look at an example. So let's look at an example of how we do this. So the particular example I want to look at is our canonical example, which you should have a sheet I handed out earlier, which has the canonical example on it. So we had a sheet with canonical examples. And so let's go to a canonical example, where we have 3 CSTRs in series. Look at your sheet and tell me what is GP. What is GP? Yes.
Negative beta tau over 1 plus S tau.
I can't hear you.
Negative beta tau over 1 plus S tau.
How about looking at the 3 CSTRs in series and not the 1 CSTR?
Alpha K. D.
Sorry?
D. Volumetric flow rate.
What is GP? What is GP for this system?
Alpha times K times B.
No. No. What is, we've only done this example 300 times in class. What is GP? Yes? Hello? With the green computer? What is GP? I can't hear you. What is GP for 3 CSTRs in series? One plus ST? Everything. Power 3. Your job, if you want to learn, if you're interested in learning, is before you come to class, you reviewed all the notes from previous classes. I've done this example at least 6 times in class. If you're looking at me like you've never seen it before, then you're setting yourself up to fail the final. If you want to learn, you come to class prepared to learn. The way to come to class prepared to learn is to know what we did in previous classes. If you don't, that tells me you're not interested in the material and you're not interested in getting a good grade. The problem is, it's not just your grade, but when you go out and get a job and you have to use control, and if you don't know the basics of control, you won't be keeping your job very long. Okay, I'm going to absorb the alpha into the KP right now. So I'm going to absorb the alpha into the KP. And I'm going to pick some numbers here. So let's choose some numbers. So I'm going to assume that I have a reaction, A goes to B. And therefore T is tau over 1 plus K tau, where I'm assuming that all these reactors are the same size. V1 is equal to V2 is equal to V3. So we're going to do sort of a numerical example here. And I'm going to let SP prime be equal to 0. But I'm going to have and GS and GV both be equal to 1. So that's why I said alpha is equal to 1 in this case. And as far as the controller is concerned, I'm just going to use a proportional controller. This is proportional only. And so what am I? I'm setting up a problem that's not super complicated. And the idea here is, I would like to look at how I look at the roots of the denominator. And when you hear the denominator is 1 plus GP, GV, GC, GS. Well, and in this case, I'm going to assume that I have GD. I'm going to assume that the disturbance is also at the entrance, and the disturbance is just 1 over 1 plus ST cubed. And this was done, again, multiple times in previous classes. So we're looking at a situation where there's no SP prime. So therefore, I'm looking at this term here, GDD CV prime over D prime. So let's notice that CV prime tilde is equal to D prime tilde times something. And let's look at what it's times. So I've got a GD in the numerator, which is 1 over 1 plus ST cubed, divided by 1 plus. Okay, let's see who's paying attention. What is GP? I need a GP. What is GP? Yes, what is GP? Yeah, it's written right here on the blackboard. What is GV?
V or D? V or D?
V is in Victor. It's written on the blackboard. If you're paying the least bit attention, you would know what it is. It's just a matter of reading. 1. GV is 1. What is GC? It's written on the blackboard.
One?
No,
No, GV equals GC.
no,
I'm sorry, I guess it was GC.
AC. Okay, this is just showing me that people come here and they don't listen. It's written on the blackboard. I said it a second ago. AC. What is GS?
KP.
wait, no.
I said, what is GC? GC is AC.
Oh, okay.
And what is GS? 1. GS is 1. Okay, so I would like to multiply this out so I know what the denominator is. So I've got D prime tilde. And remember, D prime tilde is this F tilde of T. I'm only interested in what's underneath here. So when I multiply this out, so I don't worry about, this is that F, I don't worry about this. And I'm going to multiply top and bottom by 1 plus ST cubed. So if I do that, I have a 1 in the numerator, and in the denominator, I have 1 plus ST cubed plus KP KC. So let's multiply that out. That's S cubed T cubed plus 3S squared T squared plus 3ST plus 1 plus KP KC. Can you see that denominator, or do I have to rewrite it bigger? Then I'll just rewrite it. So again, let's just note that that is CV prime tilde over D prime tilde is equal to 1 over S cubed T cubed plus S squared times 3T squared plus S times 3T plus 1 plus KP KC. So this is all in the denominator. And notice that this thing is a cubic equation. And the coefficient of the S to the 0 term depends on KP KC. So let's look at the roots of this denominator. And let's pick some numbers so we can actually get somewhere. So let's let t equal to 5. Set t is equal to 5. And then I'm going to, what other number should I stick in here? T is 5 and various values of kc. And I think kp I'm going to set equal to 1, I believe. I didn't bother writing that, but I believe I'm going to set kp equal to 1. I didn't bother writing that down, but I believe that's the case. Okay, so let's notice what happens if Kc is 0. if I said Kc equal to 0, if I said Kc equal to 0, yeah, so once I multiply this out, if I said Kc equal to 0, then this term drops out. And then what I have in the denominator is just 1 over St cubed. So when Kc equals 0, I have 1 over 1 plus St cubed. Because that's all that survives in the denominator. So therefore, if I set the denominator equal to 0, then that tells me that 1 plus St equals 0 3 times cubed. And that tells me that S1, S2, and S3 are all equal to minus 1 over t. And if t is 5, that says this is minus 0.2. So if this is minus 1/5, when I'll call that a, so when Kc is equal to 0, all 3 roots are a is equal to minus 1/5. Now what happens as I start increasing Kc? So if I increase Kc, for example, I think I had particular values, I didn't bother writing them down. So I'm increasing Kc. As I increase Kc, then I change the constant here. I'm increasing the constant here. So if I look at the roots, what happens when I increase Kc a bit is I get to b, and I get 3 roots. So when Kc, I forget the exact number, when Kc is 0, then all 3 roots are minus 1/5, minus 1/5, minus 1/5. When I take Kc a little bigger, greater than 0, then what happens is one root becomes, we'll call this b. One root stays real and negative, and it's more negative than a, but 2 other roots split up and become complex conjugates of each other. And we know that that has to be the case because since the coefficients of this cubic are real, whenever I have one complex root, I need another complex root that is complex conjugate so that when I multiply them out, I can get real coefficients here. So therefore, I could only have even numbers of complex roots. And one of them, so if I have 3 roots, one of them, at least one of them has to be real. As Kc gets bigger, even bigger, Kc is going up, I go to C, D, E, and when I get to Kc is 200, for this particular example, then I get to F, where F is here. And let's see what happens at F, where this is the axis. So this is the imaginary axis. So let's notice that in this case, where all 3 roots are minus 1/5, the system is stable and overdamped. Stable and overdamped means it looks like this, like one of these 2. That I only have exponential decay. However, once I get to B, situation B, I have the real part is negative, but the imaginary part is non-zero. The real part is negative, but the imaginary part is non-zero. So it looks like this. So these are all stable all the way through E. These are stable and underdamped. F, however, is a situation where in F, I have what's called neutral stability. What's going on there, or actually it's called marginal stability. Marginal. So what that tells me, remember I have 3 terms in my solution. When I do the inversion, I'm going to have 3 terms, each one of which is multiplied by an exponential. And what we find here is one of the terms is going to decay exponentially. The other 2 terms are not going to decay exponentially. The other 2 terms are simply going to oscillate because they have real part 0 and imaginary part non-zero. So that's marginal stability in that the output doesn't grow, but it also doesn't shrink. It just oscillates. And finally, when I get to a higher value, say PC is 250, G, then I move out here. And G, we have simply unstable. Because in G, we have A greater than 0 and B less than 0, B different from 0. So here, the real part is crossed over the imaginary axis. So you can see it's critical. What we've done is we've followed the roots as we've changed this one parameter, Kc. We've changed the parameter Kc, and we follow the roots. And this is called root locus. This method is called root locus. In case you didn't know, the class started 45 minutes ago. Is there any reason that you're coming 48 minutes late?
Yeah, I was busy. Yeah, there's no problem, I was busy.
Okay. So this is called root locus. And this is a direct way of trying to trace the stability of the system as the parameters change. And this worked, yes?
Is there a reason why you give t equals to 5, or is this an assumption?
You have to pull your mass down.
Is there a reason why you said t equals to 5 and b equals to 1, or you just made?
No, I wanted to give you a numerical example. I could pick any value, but just so I could actually put numbers in, I chose t is equal to 5 and kp is equal to 1. You can choose any numbers, but I wanted to give you a numerical example so that you can see what's happening in a particular example. Any other questions? So now this, of course, this method called root locus works great for a single parameter because I only had to do calculations for changing one parameter, Kc. But let's say I have a PID controller. If I have a PID controller, I have 3 parameters. I've got Kc, Ti, and Td. And to actually use this method for a system where I have more than one parameter, I'd have to explore a 3-dimensional parameter space. And you could imagine that that's going to be much, much more computationally intensive, and often it could be impossible to actually carry out because it's so intensive. So what do we do in situations like that? And what I'd like to show you is that there are plenty of things we can do. And we're going to concentrate on various different methods. So there are 4 methods that we typically use. There's root locus, there's something called Bode plots, there are Nyquist plots, and then there's also a 4th method that which is called Routh-Horowitz. So what we can say here is that the Bode plots and the Nyquist plots are graphical. Whereas Routh-Horowitz and root locus are computational. The methods that what are the criteria for the methods that we like? We would like methods where the calculations are not too complex. Obviously, root locus is fine calculation for a single variable. But if we have multiple variables, multiple parameters we have to explore, that calculation's again too complicated. We'd like the methods to be useful for many systems. We'd like it to tell us how stability of the open loop system affects the stability of the closed loop system. That is, if we know about the stability with no control, what does that tell us about the stability with control? Like the example I just erased here. And we'd also like to know how the process characteristics determine the tuning constants, which is what we have here. Why do we get things that look like this? So those are the criteria, and we're going to concentrate in this class on root locus for simple situations and Bode plots. We're going to leave the Nyquist plots and the Routh-Horowitz. Routh-Horowitz requires a much more calculation, and the Nyquist plots are more complicated, we're going to focus, especially since it's already December 1st, and we have, I believe, after today's class, we have 4 more classes. So we're going to focus on the Boudet class. And this is actually quite important. So it's a shame that we only have half the class here. But you know, people make their choices of priorities. If they don't find this course a priority, they won't get a good grade. Okay, so let's take a look at that. What's the idea of the Boudet stability method? So here, this is sort of, I'm going to give you the idea, and then we're going to do some calculations, but the idea is really the central thing. And let's think, first of all, let's define what we mean by open loop. So by open loop, the idea is we open the system here. So when the system is open loop, the CVM, prime tilde, doesn't get fed back to here. That's the open loop system. The closed loop system is where the feedback actually happens. So let's consider the following experiment. Step 1, open loop. Step 2, make SP prime M sine omega t. So in this case, I have a sine function coming in. This is pink. Might be easier to see than the orange. So I have a sine function coming in. I want you to stop me and ask if there's anything we don't follow, because it's important that you understand the concept here before we start writing equations. Now, we know, because our system has been linearized, all the models are linear, that when I have a sine function coming in, so that immediately, since there's no CVM, that means E is a sine function, because it's just SP prime. This becomes a sine function. Nothing's changed here. When it goes through GC, GV, GP, all linear, CV prime and its measurement is also a sine function, but it may have a difference in phase angle. So this is still a sine function, but it may have a different phase angle. Is that clear? Sine in, sine out, but so the in, at this point, CVN prime might be proportional to, well, equal to an amplitude ratio times the sine of omega t minus phi. So there might be a phase angle, phi, phase left. Now what I'm going to do is at the same time I'm going to close the loop and set SP prime to 0. So I have the sine function in the system, but now I'm going to close the loop and set SP prime equal to 0. But before I do that, maybe I should say this is 2A. 2A, I'm going to tune the parameters so that phi is equal to minus pi. I want phi to be minus pi. You'll see why in a second. So that says, when phi is minus pi, that says, so why don't I erase 3 and rewrite it so I have a little more space. When I tune this, so what does that mean? That means if the input, SP prime, is a sine function, then CVN prime is exactly 180 degrees out of phase. So delta phi is minus pi. Is that clear? They're exactly 180 degrees out of phase. Okay, so now I close the loop and set SP prime to 0. So I have the sine function in the system. It just came around the loop. I've now closed the loop, and I'm not adding anything else with SP anymore. SP is 0. So what happens? CV, now, whatever I had here, all of a sudden, that is now multiplied by -1. So when I multiply it by -1, -1 times CVM prime now becomes the sine function again. That is, this now, minus CVM, is exactly in phase with the sine function. It's exactly in phase. So this is now in phase with original sine function. So that tells me that when I take SP prime minus CVM prime, the peaks add and the troughs add. So instead of, so what does that mean? That means when I go around the loop, this gets multiplied by the magnitude of the original sine function, gets multiplied by the amplitude ratio. And it gets put in as a positive quantity here, because it was 180 degrees out of phase, now it's in phase. And every time through the loop, it gets multiplied by another amplitude ratio. So what does that mean? That means, so when it goes through the loop, around loop once, when I say it, I mean the sine function, goes around the loop once, it stays in phase with the way it started. But multiplied by the amplitude ratio, AR, of all the G's that it went through. It started here, went through GC, GV, GP, GS, so now it got multiplied by the amplitude ratio of that product, by the amplitude ratio of GC, GV, GP, GS. So what does that tell me? That sine function, it started out as sine, let's say, of magnitude 1. It goes through the loop once. And when it comes back here, it's still a sine function, but it's multiplied by the amplitude ratio of GC, GV, GP, GS. So it's still a sine function, but now it has a magnitude amplitude ratio times 1. But it's the same sine function, just either bigger or smaller. When it goes through the loop again, it gets another factor of the amplitude ratio. And as it goes through the loop 1,000,000 times, it's multiplied, it stays through, every time through the loop, it stays a sine, but is multiplied by the amplitude ratio. And for n times, so n times through the loop, means it's multiplied by amplitude ratio to the nth power. So what does that tell me? That tells me if the amplitude ratio is less than 1, then a fraction to the nth power as n goes to infinity gets smaller and smaller. So AR to the n as n goes to infinity goes to 0. So that's stable. But if the amplitude ratio is greater than 1, then AR to the n, as n goes to infinity. And that's unstable. So if I have a sinusoidal perturbation, and every time through the loop, it's unchanged and it gains another power, another factor of the amplitude ratio. The amplitude ratio is what determines whether the system's going to be stable or not, whether this sine function is going to explode or it's going to die out. And it's the amplitude ratio of GC, GV, GP, GS that is one loop cycle through the system. And we call that GC, GP, GV, GS, we call that G open loop, OL. And it's the amplitude ratio, the AR of interest is the GOL of I omega. That's what we need. That's exactly what we're looking at. Are there any questions on that? Now, what are we assuming here? What we're assuming is that in order for this to make any sense, for it not to be obviously unstable, if G open loop itself, if the amplitude ratio is infinity, if G open loop is unstable, then the system's unstable. So to even bother with this, we assume that GOL is stable. Because if it's not stable, then we don't even have to do this. It's clearly unstable. And the other thing we assume is that phi is monotonic after minus pi. And it's monotonic in omega. Now when I say we tune this. If you remember, we tune the phase lag to be minus pi. How do we tune the phase lag? Remember the phase lag, so let's just go back and see how we do that. The phase lag, phi, remember phi is the arc tangent of the imaginary part of G over by omega over the real part of G over by omega. So I don't tune it by changing parameters because I want to study the stability for a given parameter, Kp, Kc. I can tune it by changing omega. So I change omega, I change the frequency of the sine function in order to tune the phase lag. So I tune this, it's not the parameters, but I tune omega so that phi is equal to minus pi. And now you see why earlier in the semester we did the Baudet plots. If you remember the Baudet plots, we plotted the log of the amplitude ratio versus the log of omega, and the log of phi versus the log of omega. And if you remember, what's going on here? So you can, if you remember, some of the curves look something like this. And we'll go into some detail there. Let's say the curves look something like this. If this value is 1 here, and let's say this is, say, minus pi. So how would we use this method in calculations? Well, the first thing we would do is we would look for an omega that gives me minus pi. That's omega critical. I'll call it omega critical because it gives me a value of phi that's minus pi. That's exactly tuning omega so that phi is minus pi. And then at this value of omega critical, I would go up here and say, well, what is the amplitude ratio? So at minus pi, I go this way. I look here, look for omega critical, go up, find, and then go across here to find the actual amplitude ratio. Now, if 1 is up here, then I'm safe because this is less than 1. But if 1 is down here, then I'm in trouble. Then it's unstable. The other thing you could notice, if this curve is monotonically decreasing, then if this curve is monotonically decreasing, then if omega critical moves to the left, if omega critical were, so if this is not minus pi, but if this is minus pi, so if I have an omega critical further to the left, well then I'm further up on the amplitude ratio curve. So you could imagine anything that, when curves look like this, if I reduce omega critical, I make the system less stable. If the curves look like this. And if you remember, the curves did look like this for some simple systems. So why don't we just remind ourselves of a couple of things about complex variables, well, or about these quantities when I have a product. So you notice that I'm interested not in one of these g's, but in the product. So let's recall that a g, say of I omega, because that's something I'm going to need, g of I omega is a complex number. This is a complex number. So I could write it as a magnitude, g of I omega, times e to the I phi, where this is the magnitude, which is also the amplitude ratio, and phi is the phase length. Now what happens if I have a product of these g's? So if I have a product, g open loop, is a product of gi's. It's a product of g's. So let's notice when I take, this is equal to the magnitude of the product times e to the I phi of the product. Well, let's see what that is. The magnitude of the product, g open loop, is the product, the magnitude of the product is the product of the magnitudes. Product on I. And if I multiply e to the I phi's, a bunch of e to the I phi's together, then I get e to the I times the sum of the phi's. Maybe I should use J here. So what we see here immediately is that when I have a product of 4 g's, then the amplitude ratio of the product is just the product of the amplitude ratios. So it's really easy for me to calculate this amplitude ratio that I need. The amplitude ratio of this, I can get it from the individual amplitude ratios of GC, GP, GV, and GS. I just multiply them together. And I can get phi for the whole thing by taking the sum of the phi's for the individual ones. And that's nice because when I multiply them together, I can get some complicated mess. But if each one of them is not too complicated, I can just get the amplitude ratio and phi for each one of them. And then I could add the phi's and multiply the amplitude ratios. Any questions on that? So, any questions on that? All right, well, why don't we look at a particular example? And let's look at a first order system. Again, why do I notice this? First of all, in your textbook, I think it's figure 10.13, or no, 10.4. No? Maybe it's 10.13. I don't remember where. In your textbook, in chapter 10, there's, for a number of sort of typical systems, first order, second order, they show you, they make these plots. They show you what these plots look like, how the amplitude ratio depends on omega, and how phi depends on omega, for a first order system, for a second order system, for proportional only, for proportional integral, etc. So you can see what those look like. And what you can see here, again, is, remember what I hinted at here, was that if I move omega critical to the left, then I'm gonna make the system less stable as long as this is monotonically decreasing. As you'll see, we can see if I'm going to move things to the left by just adding the phi's. If one of the phi's that I add is negative, if one of them is negative, then I'm going to be changing the scale of the overall phi, because I'm going to make all the numbers here more negative. Okay, well, let's look at a first order system. So if we look at a first order system, here we go. We have an example where we have a tank. And again, I have an input here. And I measure what comes out. And if I don't like it, I adjust this flow rate. So this is a mixer with proportional control. So here I have a CSDR mixer with proportional control. So here I analyze what comes out, and I have a stream coming in that had from a different part of the plant. If it doesn't have the right concentration of my reactant, of A, because I would like a lot of A, then I can spike it with more A. So that's basically how it goes. And if you work, this is an example that we've looked at before. And let's notice that this is a first order system. So GP, because this is a first order system, is equal to KP over 1 plus ST. It's a first order system. And what I'm going to do here is I'm going to choose numbers. Again, so that I can give you a real example. So let's let Kp be equal to 0.039. And T be equal to 5 minutes, right? T be 5 minutes. And where are we? And what else do I want to set here? Yeah. Okay. So in this situation, I'm going to set GS and GV equal to 1. So what is GP? So GP, GV, GS, and it's proportional control, so I have that GC is AC. This is 0.039 over 1 plus S times 5. So this is a first order system. And what do we have in a first order system? In a first order system, we have that the amplitude ratio here. So we also have a KC. Yeah. So with GC, I also have a KC. And what I would like to do is remember that this is a first order system, and we did in great detail, we came up with the Baudet plots for first order systems. So the Baudet plot, if you remember, when I have 1 over 1 plus ST, well, G tilde, G of I omega is equal to 1 plus I omega t. And in order to get the amplitude ratio, and well, in order to get the phase lag, I have to multiply by 1 minus I omega t over 1 minus I omega t. And if I do that, I get 1 minus I omega t divided by 1 minus I squared plus omega squared t squared. So if I look at the magnitude of G of I omega, this was equal to, and we did this calculation earlier, it was the square root of 1 squared plus omega t squared over 1 plus omega squared t squared is 1 over the square root of 1 plus omega squared t squared. Similarly, the amplitude ratio is the arctangent of the imaginary part over the real part. The imaginary part is minus omega t over this, and the real part is 1 over that, so just minus omega t. And therefore, when we plot the log of the amplitude ratio versus log of omega, and the log of phi versus log of omega. Let's see what we get. Well, the log of this versus I omega, when omega goes to 0, this goes to 1. 1. So it's going to asymptote to this because omega 0, the log of omega is minus infinity. When omega goes to infinity, the 1 becomes negligible, and the square root takes the square root of the square, and I just have 1 over omega t. So when I take the log versus the log of 1 over omega t, I just get minus omega. So I get something that looks like this. It becomes a straight line of slope minus 1. Exactly as I had over here, something that looked like this. Similarly, and now if I look at the arctangent. The arctangent, we say, again, the arctangent looks something like this. The arctangent, when omega goes to 0, the arctangent of 0 is 0. And the arctangent of when omega goes to infinity, the arctangent of minus infinity is minus pi over 2. So those are my two curves. And remember what we said, the first thing we want to do is, can we tune omega so that phi is minus pi? Well, you can see here that no matter what we do to omega, for a first order system, phi never gets below minus pi over 2. So this system is stable, because I can never get to minus pi. What we're going to do next time, since I'm essentially out of time, is we're going to look at a second order system. And what we're going to see is that for a second order system, which we also did this calculation for before, in a second order system, you also never get to minus pi. But in a third order system, and the way we'll get a third order system is we'll take a GS and a GV that are both first order. Once we get to a third order system, the phi's will add. Each first order system never gets below minus pi over 2. But if this is first order, this is first order, and this is first order, then I have the possibility to get to the minus 3 pi over 2. If I can get to minus 3 pi over 2, I can get to minus pi. And then we'll look in the third order system how we actually use this method here. So we're going to do that next time. Are there any questions on that? Make sure you sign the attendance sheet, because anyone who didn't show up today is getting punished. And I will check the other attendance sheet